So good evening everyone. So this is third week of live interactive session, and in this session we will be talking morely about precipitation. So in the last week we talked about atmospheric water, and by the end of the atmospheric water we learned like how the formation of precipitation was being done. So in today's class we'll be talking about precipitation. So the first thing that we'll be covering in today's session is we'll talk about thunderstorm cell model. So what is thunderstorm cell model? We'll learn that. We'll use a derivation for that. Then we'll look into some problem based on thunderstorm cell model. Then we'll discuss about what are the different forms of precipitations. Then how can we measure the rainfall, which is one of the type of precipitation. Then we'll look into rain gauge network, where we'll discuss about whether the number of rain gauges available in a catchment is sufficient or not. Then we'll see how we can present the rainfall data. There are different ways of representing rainfall data. Then we'll then we'll do about the analysis of rainfall data. Here we'll talk about how we can check the consistency of data, whether the data set that we have is consistent or not. If there are any missing value, how can we overcome that, or we can analyze that missing value from the rainfall data. At the end we'll also look into how we can if there is a spatial distribution. We all know rainfall has some spatial and temporal variability. So how to account for spatial variability? There are three different approaches that we'll look into, and by the end of the session we'll also discuss the assignment 3, and I've also prepared some sample question for practice. So this is what we are going to do in today's session. So we'll start with the first part, which is thunderstorm cell model. So first we should look like why there is a need for such kind of a model, or what is the need of, or what is the purpose of thunderstorm model. So the thunderstorm model, the thunderstorm cell model is used, the thunderstorm cell model is used to determine the rainfall intensity. Determine the rainfall intensity, and we call rainfall intensity as small I. So how does this work? So let us know, in the previous class when we were talking about atmospheric water, right? So we have studied about precipitable water inside a water column, right? So there we understood that there is difference in pressure at the ground surface and at an elevation, as also there was difference in temperature at the ground surface and at an elevation. So we have studied like how pressure and temperature varies with respect to altitude. The similar kind of thing we are going to study here as well. So there are different atmospheric parameters, right? We have pressure with us, we have temperature, we have specific humidity QV, then we have density of air, and then we have velocity, right? So all these parameters, they do changes at ground surface and also at the elevated surface. So what we can do is, along the ground surface we can measure this thing, and in order to calculate the same value at any other surface we can use thunderstorm model. So on what principle does thunderstorm model work? So it works on the principle of continuity equation. So if you have watched the video, you would have seen like there was a derivation, like based on Reynolds transfer theorem they have derived the thunderstorm model, and they have calculated the equation for rainfall intensity. So that derivation we are not going to see, but we are going to just see what is the basic of thunderstorm model, and at the same time we'll also solve the numerical on it. So if we look into a thunderstorm model, so if we want to look at the representation diagram for this, we can say like something like this. Column we have, and this is the ground surface. So the parameters, like if you want to say the pressure, the temperature, everything is known to us at the inflow region. So inflow region is nothing but the ground surface. This is the uplift region. Uplift region means where the warm air will start rising inside the column, and it will, as it travels upwards, the temperature goes on decreasing, it becomes cold and condensation will form. So this is the outflow region. So we can say that a thunderstorm model is divided into three regions: the inflow region, the uplift region, and the outflow region. So it is divided into three parts. So as I said, At the inflow region, the moist airs are warm, the temperature is more, but as it starts uplifting, the moisture starts becoming cooler. It means the air is getting condensed, and at the outflow region, the air is much cooler, and it comes down again into the cell. Again the process keeps on repeating. So this process which keeps on repeating, it's called as convective circulation. So in the previous class we have studied atmospheric circulation, right? But in today's class we have discussed about convective circulation. So this entire process is called as convective circulation. Then using Reynolds transform theorem and continuity equation, what we can see is we can derive a equation for rainfall intensity, and that equation is something like this. So the equation for rainfall intensity using Reynolds transform theorem is small I is equals to 4 times of dry intensity at 1 into wind velocity at 1 into delta of Z1 divided by density of water into capital D into specific humidity of 1 minus specific humidity of 2 divided by 1 minus Q of 2. So this is the equation which is used to calculate the rainfall intensity using a thunderstorm model. So for the derivation for this has been already, you would have seen the video, so I'm not going to cover the derivation here, but this is the equation which you are going to use. So the next like now we know the equation, now we should look at the numerical, like how to solve rainfall intensity if we have some numerical with us. So let us see at an numerical. So this is the equation, right? We have seen. So let us see an example. So this is the question that we are going to discuss. So they are saying that determine the precipitation centimeter per hour. By looking at the unit, we can say that this is nothing but rainfall intensity. So they are asking us to determine the rainfall intensity from a thunderstorm cell having 3 kilometer diameter. So they are given us the diameter as 3 kilometer. It means the capital D value is 3 kilometer with a cloud base of 700 meter and an average outflow elevation of 9.5 kilometer. The surface air temperature is 28 degrees Celsius, pressure is 103 kilopascal with saturated air condition, and wind speed is 2 meter per second. Assume lapse rate of 6.5 degrees Celsius per kilometer. So if we look at the given data set that we have all these values with us. Now what we are going to do in the next step is, we'll look into the equation of I and we'll calculate the parameters that are unknown to us. So if you look at this equation, we don't have specific humidity value. We don't have QV1, we don't have QV2. But we know what is the formula for QV1 and QV2. So how we can do that? QV1. So here 1 means at the inflow region, that is at the ground floor, at the ground surface. And Q2 means at an elevation. So that elevation could be 700 meter. That is the cloud base. So the simple thing is to use all this equation which we have used during atmospheric water. So if we know the temperature at ground surface, which is 28 degrees Celsius, and we want to calculate the temperature at an elevation of 700 meter, we can use this equation, right? We want to calculate T2, T1 is known to us, alpha is also given, and difference in elevation is 700. Similarly, we know pressure at ground surface, which is 101 kilopascal. We can calculate pressure at 700 meter. The other variables are known to us. Then we can calculate the air density at elevation. Since pressure at P2 is known to us, T2 is known to us, so rho A2 would be P2 upon RA into T2, right? And then similarly also we can calculate vapor pressure E2, and using vapor pressure we can calculate specific humidity at the ground surface as well as along 700 meter from the ground surface. So if we look at this table, the first column we have divided the Z value, that is the difference in elevation, 0, 700, and at the end it is 9500. And we know the temperature at ground surface. We know temperature is 28 degrees Celsius. We have converted it into Kelvin because whenever we are calculating air pressure, we want temperature to be in Kelvin. Then this power term, if you want to calculate and keep, you can do it, but it is not needed at the ground surface. The air pressure is given to us, Air density is given to us. Vapor pressure E. I think vapor pressure is not given to us, but we can calculate since we know the value of temperature. Because we know the value of temperature, which is 28 degrees Celsius, we can calculate vapor pressure, and also at the same time we can calculate specific humidity since we know vapor pressure and pressure value with us 103. So we can use the equation QV is equals to 0.622 into E upon P. So we know E and P, we can calculate QV. So all this calculation we have done at the ground surface. Now what we are going to do using the above equation, this 5 equation we are going to calculate the same parameters at the elevation of 700 meter. So that we have calculated here all this value, and similarly we have calculated for the third region, and at the end what we are going to do, we are going to take the average of all the three and we are going to get the precipitation intensity. So the precipitation intensity that we are getting, it is in meter per second, but what unit they have mentioned in the question, they have mentioned centimeter per hour here. So using the same, since we have calculated in meter per second, you can convert it into centimeter per hour, right? So that they have shown here in meter per second and in centimeter per second. So this is how we can solve a thunderstorm cell model. Just we need to do is we need to remember this equation and use the basic of our previous class. So now that we have understood about the thunderstorm model, the next thing that we want to cover is what are the different forms of precipitation that are known to us. So let us see the different forms of precipitation. So now we are going to talk about the different forms of precipitation. So the different forms of precipitation depends upon the size of rainfall, right? So the first will start with the smallest, like the tiniest liquid water droplet that is known. It is called as drizzle. The first form of precipitation is drizzle. So as I said, it depends upon the size. So we should remember every form of precipitation with respect to its size. So the size of drizzle is less than 0.5 mm. So a precipitation with a size less than 0.5 mm is called as drizzle. Also it has a specific characteristic, like its intensity. Its intensity is also very low. Its intensity is less than 1 mm per hour. Here we are talking about 1 mm per hour. Then the next is rainfall or rain, right? So again the rain, it has different, the water drop of rain is of different size. So the size of rainfall varies from 0.5 mm, which is greater than drizzle, to 6 mm, and also it has different intensity. We can classify the rain as moderate rain or heavy rain, or you can say it as light rain, depending upon its intensity. Let us say if the intensity of rain is between 0 to 2.5 mm per hour, or 2.5 mm per hour to 7.5 mm per hour, or greater than 7.5 mm per hour. So based on this we can say that the rain is light rain, or moderate rain, or heavy rain. So here, by looking at the intensity, we should know that 2.5 mm per hour, call it as light rain. So if we want to call any day as a rainy day, we can say that if we have an cumulative rainfall of 2.5 mm at any day, then only we can call this as a rainy day. If the intensity is more than 2.5 mm per hour, or the cumulative rainfall is at least 2.5 mm in a day, we can call that day as a rainy day. Then the next form of precipitation is glaze. Now first we have looked into the liquid forms, right? So drizzle and rain intensity, rain both are in liquid form of precipitation, but now we are going to look into the solid form. So the glaze is the first precipitation which we can call it as a solid form. precipitation. So it is nothing but it is a ice coating. Whenever we see a coat of ice along the ground surface, we can say that that is nothing but glaze. But also it has a certain characteristic. So that specific that characteristic is nothing but its specific gravity, S. So the specific gravity of ice is between 0.8 to 0.9. Then that kind of precipitation is called as glaze. The next is, after glaze is rain. So what happened here is the specific gravity is going on decreasing. It means the density is going on decreasing. So for rain the specific gravity is 0.2 to 0.3. Also it is white opaque in color. It is white opaque deposits. Then the next is very familiar to us. It is known as snow. So the snow is of two different types, right? It could be like sand particles, or it could be like kind of cotton. So the snow is of kind of two type, like cotton or like sand. So what does it means? Like cotton means it won't accumulate. But if it is like kind of sand, it will accumulate. And the last is something called as hail. So this is we can say that it is kind of dangerous, right? Because it is kind of bigger in size. It appears like ball like appears. Its appearance is ball like appearance, and its size is more than 5 mm. So all these are nothing but different forms of precipitation. So we first started with the solid liquid phase. So in liquid phase the precipitation is under two types. First is drizzle and next is rain. So drizzle is the smallest tiniest particle of water droplet which is less than 0.5 mm, and also the intensity is very less. But when we talk about rain, the rain varies from 0.5 mm to 6 mm, and also its intensity varies. So based on its intensity we can classify the rain as light, moderate or heavy. Then we looked into the different forms of precipitation which are in solid form. So the first we started with glaze, which is nothing but ice coating. Its specific gravity is more. Then we looked into rime, which means the deposits are having white opaque color appearance and the specific gravity is less. Then we talked about the most familiar one, which is snow. So snow could be of like cotton. When we see like there is a snowfall, it could be like kind of cotton or like kind of sand. It depends upon whether it is accumulating or not. If it is accumulating, then we'll say it is like sand appearance, and if it is not accumulating, we can say that it is like cotton. And the last is the hail, which is kind of dangerous since it has bigger because its size is more than 5 mm. We can say that it is the dangerous one. So these are nothing but the different forms of precipitation. Now we are going to look into measurement of rainfall, like how we can measure this rainfall. So we have covered different forms of precipitation. Out of those precipitation, now we are only going to focus on rain or rainfall. So here we are going to look into what are the different instrument or different ways or different techniques are used which are used to measure rainfall. So first we are going to look into measurement of rainfall based on instrument. Yes, Nagesh. Yes, Naga. Do you have any question? Hello.
Understand.
Yes, Nagesh.
Sir, the question regarding in the assignment question, when the rainfall falls to the air with at the sub-freezing temperature forms, it is a drizzle or like a snow.
Um, Naga, what we usually do is we cover the assignment question towards the end of the session.
Okay, okay, sir.
So by 8:45 or 8:40, I'll be coming on to the assignment questions.
Okay, okay, sir.
Okay. I'll cover this
Okay,
question like the answer I can tell now, but by it will be good like if we cover at the end of the session.
Okay, okay, sir. Thank you,
Okay.
sir.
Okay, now.
Okay, thank you.
So now what we are going to do, we are going to cover the different ways of how we can measure the rainfall. So the first one is by using instrument, and that instrument are called as rain gauges. So there are two different types of rain gauges which are there. You can look on the screen also. One is called as non-recording rain gauge and the other is called recording rain gauge. Right? So what is the difference between the two? So first let us look on to the non-recording rain gauge. So non-recording, by that word itself we know the rain gauge is not recording the rainfall by itself. We have to do it manually. So how you can do, you want to measure the rainfall. So what you can do, let us say there is a rainfall event happening. So let us say there is a rainfall event that is happening. So how does the non-recording rain gauges work? So look at the setup here. It is the simplest setup, right? We have seen like how funnel we already know like what is funnel, what it will do. It will collect the rainfall and it will transfer it onto the collecting bottle. So we should first know like at what period does we record the rainfall. So the rainfall is recorded to maintain the uniformity along the India at 8:30 a.m. in the morning. So we start recording the rainfall from 8:30 a.m. of the morning, and towards the next day we collect the rainfall and we measure it. So let us say we have a rainfall event. So for the complete 24 hour we'll collect the rainfall and we'll manually record like what is the depth of rainfall inside the bottle, since we know the volume of bottle. So we can easily calculate the volume and then we can calculate the depth also. So this is nothing but non-recording type of rain gauges, but there is some problem. Obviously it is going to since it is a manual instrument, what is the problem? Let us say that if the rainfall is very high in a particular day, so if the capacity of what it can happen that the capacity of bottle could be completely filled, so in that case you have to again replace the bottle. So that kind of problem could be there. So the next type of rain gauges comes into handy. So the next type of rain gauge is recording rain gauges. So here if you don't have to go and do the manual work, the rainfall is itself sufficient, capable to record the rain gauge. So there are three different types of recording rain gauge. The first is weighing bucket, right? The next is tipping bucket, and the last is floating, or it is also called as natural siphon. So weighing bucket and natural siphon, they both work on the same principle. So I'll cover weighing bucket, and the similar kind of work is done by natural siphon, right? So I'll only discuss about weighing bucket and tipping bucket. So let us look into weighing bucket. So if you look at the arrangement on the right hand side of the weighing bucket, what do we have here is we have a balance linkage mechanism, and to that balance linkage mechanism a pen is attached, and then that pen is attached to a revolving drum with chart. So what happens is once the precipitation enters the funnel, it starts filling the bucket, and once it fills the bucket, the weight of bucket keeps on increasing, and since the weight of bucket increasing due to the balance linkage mechanism, it will get drop and the pen will start rotating on the drum, and what we will get is we'll get a plot, and that plot is nothing but it is accumulated rainfall versus time. So you have a 24 year 24-hour data, like on the graph here you will have a 24-hour data series. So it will, what will happen is you will get the accumulated series of rainfall by the end of the 24 hour. So this is one of the important outcome that we get from weighing bucket. So remember, this weighing bucket gives us accumulated rainfall for the entire 24 hours. The next is tipping bucket. So what happens in tipping bucket is, here if you look at this, there is a bucket inside the arrangement, and what happens is the bucket is having a there is combination of two buckets. What happens is the rainfall will enter either of the bucket, and once either of the bucket, let us say there is the bucket in the left hand side is collecting rainfall, and it collects a rainfall of about 0.25 mm. So what happens once it collected this much amount of rainfall, that is 0.25 mm of rainfall, the bucket will tip, and once the bucket tips, it marks some reading on the pivoted bar where there is a drum, or where there is a revolving graph, where there is a graph attached to it. So once the bucket tips, we'll get one reading. So similarly, how many times we'll get the reading? Once if this much amount of rainfall is collected in either of the bucket, it will tip. So it depends upon the intensity of rainfall. So this is tipping bucket, and as I said at the earlier also, the floating bucket works on the similar weight of weighing bucket. So the similar kind of arrangement is there, but the only thing is there difference here is it gives us mass curve of rainfall. It doesn't give us the accumulated rainfall. It gives us the mass curve of rainfall. So we will look into what is mass curve of rainfall and what is accumulated rainfall when we talk about the different ways of how we can represent the rainfall series. So we'll look into this of mass curve of rainfall. So these three are coming under the instruments, like different instruments that are used. So only there are two types, one is non-recording and there is recording. Also we have to remember this, the non-recording rain gauge is called as Simon rain gauge. So this could be asked in examination as well. Simon gauge is of which type of rain gauge? So we should remember non-recording rain gauge is called as Simon rain gauge. Then the recording gauges are of three types: weighing bucket, tipping bucket and natural siphon or floating. So these are instrument based measurement. Then there is something called as remote measurement. So what happened is rainfall, whatever instrument we are using, we are getting the rainfall for a particular location. But what if we want to cover a huge area? So in that case, we can use either radar or we can use either satellite, right? So how does radar works? So the only thing that we need to remember is the radar works like it emits pulses of electromagnetic signal which returns after it strikes a rainfall drop. And what we are measuring is we are measuring the return signal from the radar to compute the rainfall intensity. So it measures the rainfall intensity, right? Because we are calculating the time of the returning signal. So then by integrating over time, we can get the precipitation. Like if you multiply it with the total time, we can get the precipitation. So this is how radar works. So there is some limitation also. The radar can only work up to a radius of 200 kilometer. So in order to overcome this limitation, the other thing is we can go use for of satellite product. The satellite product, what it will do, it will cover a bigger scale. Then there is something called as automatic rainfall monitoring. So these are nothing but these are like tipping bucket only, but there are certain sensor attached to the tipping bucket. So what does that sensor does? It collects the information and it transfer it to your transmit the data to the station at regular intervals. So automatic rainfall monitoring is nothing but like suppose there is a remote location where we cannot go regularly, more oftenly. So what we can do, we can place a automatic rainfall monitoring or AWS there. So using that, we don't have to travel to the site oftenly. What we can do is the tipping bucket will collect the data and we have ensure a sensor to that. So that sensor will transmit the data set to our station. So these are like different ways of how like we can measure the rainfall. So the next part is now, since we know how rainfall is getting measured, the next thing is we want to know whether if we have an area, let us say there is an area of 1000 kilometers square and we have like installed 4 rain gauges there. So we would like to know whether this 4 station would be able to give us the proper representation of the rainfall or not for that 1000 kilometers square of area. So in that case, we would like to study more of rain gauge network. So what we are going to study here is we would just like to know whether the number of stations installed in a particular location, number of rain gauges installed in a locations are enough or not. So so there is an important term here known as rain gauge density. So what is rain gauge density? It is nothing but the ratio of total area of catchment to the total number of rain gauge in a catchment. So the only thing we should remember here is the number of rain gauges depend upon the coefficient of variation, and also amount how much error is allowable to the estimation of the data set. So these two things are most important when we want to calculate the number of rain gauges in any catchment. Now let us see this thing, the number of rain gauges based on the allowable coefficient of variation. So if let us say we want to know whether there is a need of extra gauge or not. So the thing is that if CV for a data, rainfall data is less than 20%, if the coefficient of variation is under 20%, we can say that there is no need of extra gauges. How many number of rain gauges is there in the catchment, they will be suffice to do the work. But what if the CV is more than 20%? So in that case, what we can do is we are supposed to add adequate number of stations. So we'll look into this with a problem as well. It would be more easy to understand. So how we can calculate CV? This is like basic, very basic. First, if we have the data set, we can calculate the mean of the data. Then you can calculate the standard deviation of data, and the ratio of standard deviation and mean will give you the CV. So this is very simple. We can calculate coefficient of variation. Now this equation here, this equation is very important. If we want to calculate the desired number of rain gauges, let us say we have a rain site where the number of existing gauges is 4, right? And they have given us the desired coefficient of variation or existing coefficient of variation, and we want to calculate what is the desired number of rain gauges in that catchment. So we can use this equation. Also, there is some standard given by WMO. Like if the area is of this much, then there should be one station. So depending upon the size of area, there should be at least one station installed. So let us look at the different areas. So let us say if the region is flat, right, then the ideal is one station for 600 to 900 kilometer square. This is the ideal, but how much is acceptable? Acceptable is 900 to 3000 kilometer. So for an area of 900 to 3000 kilometer, there should be at least one station, which makes it acceptable according to WM. Then for mountainous region, the ideal is one station for 100 to 250, but acceptable is one station for 250 to 1000 kilometers square. And for arid and polar region, one station is ideal for 1500 to 10,000 kilometers square, right? So we should remember all these values here, the standard which is given by WM. Now let us look into an example. So what they are asking is the annual precipitation at 4 rain gauges is shown in the table below. Estimate the
Sir, your screen has been not changing. Slides has been not changing.
sorry.
Sir, slide has been stuck at one point, sir. It was not changing from starting.
Okay, so what are you going? What are you looking at? Like which screen is visible to you? This
No, no, like that.
now are you able to see
No,
this screen?
no, sir, no, sir. Oh, only that portion of. Yes, sir, yes, sir.
Now it is visible.
Yes, sir, yes, sir. Visible.
Okay, okay. So now we are looking into this example where they are asking us the annual precipitation at the 4 rain gauges is 800, 1500, 1000 and 1600. So these are 4 stations. They are asking us estimate the extra rain gauges station needed if desired CV is 15%. So what we are going to calculate is, first thing we are going to calculate is existing CV. This is the desired CV they are giving us. But what is the existing CV in the data set that we are supposed to calculate? So how we can do that? We have 4 data, we can take the mean, we can take the standard deviation, and then using standard deviation and mean we can calculate the existing CV. So once we know the existing CV and we know the desired CV, an existing number of gauge stations are also known, that is 4, we can calculate the desired. So if the existing CV is more than 15%, then we can say that the desired number of stations should be more than the existing. So let us see how they have calculated. So here they have calculated the existing CV from the data set, that is 4 rainfall value. So see, they have taken the mean of the 4 data set, they have calculated the standard deviation, and also they have calculated the existing CV, which is 19.4 in percentage or 0.194. Since the existing CV is more than the desired, we can say that the more number of stations are required. So they got the number of total stations as 7, and the existing were 4. So the number of stations that are required is 7 minus 4, which give us 3. So in this way you can calculate whether the number of stations that are given to us, whether they will be able to do the work or not. So in this case, since the existing CV is more than desired CV, we would say that the number of stations that are 4 are not enough. There are need of more stations. So how much more stations are needed? So we have calculated total station as 7. So 7 minus existing would give us the extra stations. These are the optimum number of stations that are required, which is 7. So this is how you can solve any problem based on this equation. Right? So this is how about we talked about the rain gauge network. So now that we know about the rain gauge network and we know how we collect the rainfall, the next thing is how we can represent the rainfall data set. So there are three different ways in which you can represent your data, rainfall data. The first way is we know about histogram, right? So the first way is we can represent the rainfall data set with the help of a histogram. The second is we can represent the data with just a line plot, that is accumulated series. And third is called as hytograph. So there are three different ways. So we'll look into this here. I hope the screen is visible now. So here we are going to talk about representation of rainfall data. So the first way is, let us say we are dividing this representation into two heads. The first is spatial representation. Spatial representation means how we can represent with respect to space, and the next is temporal representation, that is with respect to time. So let us see how we are going to represent with respect to spatial representation. So the only way to represent rainfall data with respect to spatial representation is by using ISO height. Right? So what does ISO height does? In our basic civil engineering, like in our previous classes, we have learned about contours, right? So what does contours give us? It gives us point of equal elevation. So in the same way, ISO height gives us point of equal rainfall intensity, rainfall values. Right? So if we have equal rainfall values, we'll plot a contour with for that, and then we'll get that thing is called as ISO height. So let us say we have a catchment with us, and here at this contour the rainfall would be same. Let us say it would be 20 centimeter. Then there would be another contour. Well, along the entire contour the rainfall would be 40 centimeter. Then similarly there would be one more contour line, it will mark 50 centimeter. So then we can say that along all this point the rainfall is nothing but 20 centimeter. And this line is called as ISO height, which marks point of equal rainfall. So this is the only way we can represent the spatial data of rainfall. But if we want to give the temporal variation of rainfall, how we can do that? So there are three different ways to do that. The first is by use of histogram. The next is by use of accumulated series, where we'll use only simple line plot, and the next is called hytograph. So there are three different ways. So let us see one by one. So the first is rainfall data by use of rainfall data by simple histogram. So what will histogram tell us? So histogram will tell us rainfall depth versus time. The plot of histogram is between rainfall depth versus time. So let us say we have time in days. We have a week, 1 week data set. So first day, second, third, fourth, fifth, sixth, and seventh. So this is a week data set of rainfall. So we'll have the rainfall value for each day, and that rainfall means we are measuring the depth of rainfall here. So it would be something like this. Depending upon the value for each day, we'll get a histogram. So the key thing is to remember, histogram will give us only the depth of rainfall over a particular time. The next is, second is rainfall mass curve. So if you remember when we were discussing about recording rain gauges, so there were two recording rain gauges, right? The first was weighing type, which gave us the accumulated series, right? And the second was tipping bucket. And what does tipping bucket used to give us? It was giving us mass curve. So I told us like mass curve we will be discussing in the session ahead. So this is what mass curve gave us. So what does mass curve give us? It gives us the accumulated series of rainfall. accumulated rainfall versus time. So what does accumulated rainfall here means? Let us say we have again rainfall data for a week. So the first day rainfall, the rainfall value was 10 centimeter. And let us say the second day the rainfall value was 12 centimeters. So what does happen? The value will get accumulated. So it will always be a rising curve. So whenever you plot a rainfall mass curve, you will come into a conclusion that the rainfall data set or the curve is always a rising curve because you are plotting accumulated rainfall. So individually the value would be something like this: 10, 2, 4, it could be again 10, 8, 6, 5. But you are going to plot the accumulated, so the next value would be 12, then it would be 16, 26, 26 and 8, it would give us 34, 40 and 45. So if we plot this, we come into conclusion that it is a rising curve. So this curve is called as mass curve, which is nothing but accumulated rainfall versus time. And the last is hyetograph, rainfall hyetograph. So the first was histogram, it was nothing but normal rainfall value versus time. The second was mass curve, which gives us accumulated rainfall versus time. Now the last thing is hyetograph. So what does hyetograph give? So in the first part of the session, that was thunderstorm model, we were calculating rainfall intensity, right? So hyetograph gives us nothing but the rainfall intensity, which is I versus time. So rainfall intensity means how much rainfall is being accumulated over a certain period of time. So it could be over mm of or it could be mm of rainfall with respect to hour, or it could be centimeter of rainfall with respect to day, right? So that kind of plot will give us histograph. Hyetograph plot give us intensity versus time. So here there would be rainfall whose unit would be in centimeter per hour, because you are plotting intensity of rainfall versus time. So time here I have kept as hour, so it could be 24-hour duration, 1, 2, 3, 4, 5 till 24 for one complete day. So it would be something like this again, depending upon the value. The only thing that changes here is we are plotting intensity of rainfall versus time. So rainfall into hyetograph give us rainfall intensity versus time. So these are like the different ways where you can represent your rainfall data series. The first was spatial representation, where you can plot using isoheight, that is point joining line of equal rainfall. Then there are three different ways to plot your temporal representation. The first was rainfall histogram, which gives us rainfall depth versus time. Second was accumulated series versus time, which is mass curve. And the last is rainfall hyetograph, which gives us rainfall intensity versus time. So this is nothing but the different ways how you can represent or present your rainfall data series. So in the next thing that we are going to cover is we are going to analyze this rainfall data. So what happens is when we record the data using either instrument, that is recording, non-recording rain gauges. So what happens, sometimes we miss some data series, and that could be due to different reasons, right? So that could be because of there is some failure mechanism of the instrument, or there is some absence of manual recording gauges. Like in case of recording gauges, there is some error because we haven't recorded the data manually. So in order to overcome this missing data set, there are different techniques used. So there are different. One of the ways from which you can calculate this missing data is either you can take the simple arithmetic mean of the data set of the neighboring station, or you can use normal ratio method. So here I am going to discuss about three different techniques. The two are shown into the slides now, and there is one more technique which is called as inverse distance method, which depends upon, like all the GIS tool uses this technique. It is called as inverse distance method. So it depends upon how close the neighboring station to you is to your station which is having some missing data. You will interpolate the value based on the nearby neighboring station. So that approach we are going to also see using a reference, using a numerical by the end of the session. So the first we would like to cover these two techniques. The first is simple arithmetic method. So here what you are going to do is, let us say you have 5 stations with you and there is a station A which is having some missing data. So what you can do, you are going to take the mean of the 4 data set, remaining 4 data set, that is B, C, D and E, and you are going to substitute that mean into A. So here you can say that simple arithmetic method, let the missing precipitation P of X at a station X is determined using simple arithmetic mean. So this is like simplest method which is not recommendable in most of the cases. So the other technique which is recommendable is normal ratio method. So in order to use this normal ratio method, we have to know the normal rainfall value for the data series. So how you can do that? So let us see here. So we are talking about how normal ratio method is used. So in order to use normal ratio method, let us say we have 5 stations. And those stations are A, B, C, D and E. And there is a missing values in station A. So what we are going to do, these values are nothing but these are values of precipitation. So we are calling it as PA, PB, PC, PD and PE. Right? And these precipitation values are for a particular event, for a particular rainfall event. But also at the same time what we have is we have normal data series. Now what does normal rainfall data series mean? What is normal rainfall? So normal rainfall is calculated by taking average of 30-year data series. You are taking average of 30-year rainfall data. And when you do that, you get normal rainfall data. So let us say we have normal data for all the stations. So in order to use this method, the data set that you need is normal data of the rainfall. So if we have, if in any numerical, if we have this values, then only we can go for normal ratio method. Or else, depending upon the, if we have the distance value between each station, then we can go for distance power method. So depending upon the data set that we have, we can opt for the method that we would like to that we can use. So here we have all the normal data series with us. We have precipitation value for the 4 station. The only value missing is precipitation of A. So using normal ratio method, now we can calculate the PA value. So there is this equation. So whichever station is missing would come on the left hand side. So precipitation of A divided by normal precipitation of A is equals to 1 upon small m into remaining station. So precipitation of B plus normal So now the only unknown is P of A and we can calculate. So the thing to remember here is what is M. So M is nothing but number of rain gauge station minus 1. So why we are doing like this? Why we are minusing only 1? Because M stands for rain gauge station. Known rain gauges means the rain gauges whose values are known to us. So here only 4 gauge stations values were known to us. So that is why the approach is m minus 1. But if there are 2 gauge stations which are unknown, then the formula would be n minus 2. So 1 and 2 stand for how many data sets are missing. So if only one data set is missing, then n minus 1. If data sets are missing more than 1, then it would be n minus whatever number of data sets are missing. So m stands for how many number of rain gauges data are known to us. So here 4 were known to us, so m would be 4. So this is how normal ratio method works. Also the next method is the third method, which is not there in the presentation, but it is important to know. It is called as power ratio method or inverse power distance method. So this method is mostly used by GIS tool where they use interpolation technique and they calculate the value. For the same above example, that is 5 station A, B, C, D and E. Let us say value for A, that is precipitation of A is missing, and the other 4 data sets we have value. So using inverse power distance method, how we are going to calculate? So let us say there is a catchment here, and each station is placed something like this. So what do we know is we know the distance of every rain gauge from A. We know this distance, right? We know this distance. We know this distance. We know this distance. So all this distance are nothing but D of I. Means D of individual rain gauge with respect to A. So we know all this value, Di. And Di is nothing but resultant of your x and y coordinates or your lat and long from B. So how we can calculate D of I? So D of I could be calculated by using x of I square plus y of I square. So xi and yi are nothing but, if we are talking about A to B, so there would be some distance in x-axis and there should be some distance in y-axis. So that distance are nothing but xi square plus yi square, that will give us di value. Or we can calculate di square also. So we'll remove the square root from here. So di square is nothing but xi square plus yi square. Now what we are going to do, we are going to take the inverse of this distance square, and that would give us the weightage. Right? So what we need here is we needed the weightage value. So weightage of B with respect to A, weightage of C with respect to A, weightage of D with respect to A, and weightage of E with respect to A. And then we can calculate the PA value by using simple the summation of precipitation of individual gauge with respect to Wi divided by summation of Wi. It means we have calculated W of BA, we have calculated W of CA, we have calculated W of DA, and we have calculated W of EA. So all these values are known to us, and also the precipitation of B, precipitation of C, precipitation of D, and precipitation of E were known to us. So if we add all this value, it will give us the numerical. And similarly, if we take the summation of only the weightage, it will give us the denominator, and this will give us the missing rainfall at A. So this is how inverse distance power method works. So we'll take a numerical by the end of the session, but this is how it does work. Now the next thing to cover in the class is how we can take the average of rainfall. So there are 3 different ways we can do that. So the first is this 3 approach. The first is called arithmetic average, which we know. We are just going to take we are going to add the number of data set divided by number of observation. The next is Thiessen polygon method. So if we look at the equation for Thiessen polygon method, it is nothing but the weightage average. So let us say in our basic physics class we used to take centroid of any material. So we know there was some equation to calculate the centroid. So that similar kind of equation is called as weighted average, and that is nothing but Thiessen polygon. But how to form or how to do, there is certain steps. So that we'll discuss now. And the last is iso-Hittel method. So now itself when we were doing about the spatial representation, we learned about iso-height. So that method is nothing but iso-Hittel method. But there is some equation to it, how to calculate the average value. So that will look here. So the first method is simple arithmetic average. We know there are 8 gauge station, there are 8 values. We'll take the sum of that and we'll divide by 8, which will give us the simple average method. So there is nothing much to explain here. But the next method which is important is Thiessen polygon method. So there are some assumptions in this. So the first assumption is that the rainfall is same as that recorded at the nearest rain gauge. And the next is depth recorded at given rain gauge is applied out to the distance half of the next station in any direction. So these are the 2 assumptions that are there. So now how we can do that? So this is the step, right? So the first step is the whole area of region is A. So the entire area is A. Now they are saying is join the location of rain gauge by straight line to form a triangle. So there are 3 rain gauge station here, PA, P1, P2 and P3. So they have connected each rain gauge and they are representing it as a triangle. So we have done that. The third step is draw perpendicular bisector of each side. So we have taken a perpendicular bisector from 3 and we have bisected the center of P1 and P2. So this line. Then similarly we have bisected P2 and P3 side with respect to P1. And similarly from P2 we have dropped a perpendicular bisector and we have divided P1 and P3s. So we'll get a common point at the center of this triangle. So now we can say that each rain gauge is having its own area, right? That is, they are saying entire catchment will be divided into number of triangles and Thiessen polygons will be developed. So we can say that this triangle is now divided into three areas. Area is something like this P2 and this area. Then there is this area and this area. So we now know that each rain gauge is covering only this much area, the area that is known to us, right? A1, A2 and A3, this entire area of the catchment. Now they are saying compute representative area for each gauge, assign weightage for each rainfall area. So we are going to calculate the weightage for each rainfall area. How we are going to do that? We know the total area and we know the individual area. So we are going to divide individual area with respect to total area, that gives us the weightage. And then we are going to compute the areal average, right? So the areal average is nothing but precipitation value of that gauge multiplied by the area plus precipitation value of that gauge multiplied by the area and divided by total area. It will give us the areal average. The next is isoheital method. So we have already looked into this figure before itself. It joins the line having equal rainfall, right? So all we need to remember here is this equation which states that for individual area we are first going to take the average of precipitation. It means whenever we are using isoheital method, we are supposed to calculate the mean of precipitation, right? So if you look at P1 and A1, the precipitation here is 4. So we are first going to take the mean of it. Then for the area 2, the precipitation value is 5, but we are going to take the mean of it. So in isoheital method, it is important to calculate the mean of precipitation first, and then we are going to multiply it with its representative area. So now this is how they've shown here how reciprocal distance square method or inverse distance square method works. So we have already seen this. Like they are going to calculate the distance square d value, then they are taking weightage as 1 upon d square. Then by using this value, they are going to interpolate. So this can be done in GIS also. As I've told, this method is used in GIS. So these are like three different ways where we can take the average of rainfall, right? So this is all about like all the theoretical question and all the concept that was there in the week 3 that we have covered. So we started with thunderstorm model. We talk about thunderstorm model, why it is used. It is used to calculate the rainfall intensity, right? So we know the equation for that. All we need to do is we need to calculate specific humidity, vapor pressure, temperature, everything at ground surface and also at the elevation, and then we are going to substitute that into the rainfall intensity equation, which was derived using RTT. Then we have also seen a numerical based on thunderstorm cell model, right? Then we discussed about different forms of precipitation. So we have divided the forms of precipitation as liquid and solid. So in the liquid stage we talked about drizzle, then we talked about rainfall, right? Then in the solid state we talked about glaze, we talked about mist, we talked about rain, we talked about hail, and we talked about snow. So these are like the different forms of precipitation. Then we talked about then we only focused on rainfall, which is like the liquid form of precipitation. So we are only focusing on rainfall. So we start about like what are the different ways of how we can measure rainfall. So there are on the basis of instrument, there are only two instruments that are used to measure rainfall. The first is recording gauges and next is non-recording. So we first talked about non-recording rain gauge. By the name itself, it says that it is not going to record the rain gauge by itself. There is some need for manual observation, right? So we have looked into the setup of non-recording rain gauges, and we know that it is also called as Simon rain gauge, right? We also covered its limitation, like if in case of heavy rainfall period or storm event, what happens is we are supposed to refill, or we are supposed to change the collecting bottle as the rainfall is quite high. The collecting bottle there would be some case that the collecting bottle would be completely filled. So these are like the limitation. To overcome this limitation, recording rain gauges comes into picture. So there are three different types: weighing bucket, tipping bucket, and floating. We know how weighing bucket works, we know how tipping bucket works, we know what weighing bucket gives us. It gives us the accumulated series versus time. We know tipping bucket gives us the mass curve. So we have covered everything. Then we talked about radar and satellite. We know how radar is collecting data. It is sending the electromagnetic waves which gets reflected back as it hits the rainfall, and there was some limitation, like it is only used up to 200 kilometer radius. So to overcome that, we are using satellite data series. Then we also talked about AWS, like automatic rainfall monitoring. So these are nothing but, along with your tipping bucket, you are installing a sensor which is transmitting the data to the station. Then we talked about rain gauge network. Since we know, like, now instruments are used to measure the rainfall, now we are looking like whether these instruments in a particular catchment would be suffice or not to measure the rainfall. So in order to do that, we are working on simple statistic, like we are looking at the coefficient of variation of the data set. If the coefficient of variation is less than 20%, we are saying that there is no need. But if the coefficient of variation is more, we are saying that there is a need to install more rain gauges. So the simple equation here is to remember is, if we want to calculate the desired number of rain gauges, we should know the existing CV in the data set. The desired CV is given to us and the existing number of rain gauges is given to us. So if the existing CV is more than desired CV, we will say that there is need of data set. But if the existing CV is less, then we can say that the existing number of rain gauges would be able to measure the data set in the particular catchment. So we have also seen one example. Then we looked into this, what are the recommendation given by World Meteorological Organization. So for each type of terrain, that is for flat region, for mountainous region, and for arid or polar region, there are certain guideline given to us. So we have to remember these values. Then we have seen this example. Then after this, now that we have known like how to measure the rainfall, how to, whether the number of rain gauges are suffice or not, then the next thing is how we can represent the rainfall data. So there are two different ways. The first is spatial variation and this next is temporal variation, right? So we want to represent the spatial representation of rainfall data set. So the only thing to do is we are going to use ISO height. The next is to presentation of rainfall data set. So there are three different ways. The first is rainfall histogram, which plots the rainfall depth versus time. We have seen this figure before also. Then we talked about rainfall mass curve, which gives us the cumulative or accumulated rainfall versus time, which is always a rising curve. And the last is rainfall hyetograph, which gives us the rainfall intensity versus time. Then the next thing that we learned is analysis of rainfall data series. So we are doing this now to see like whether there is any missing data in the series and how we can overcome this difficulty, or how we can get this missing value in the data series. So there are many multiple ways, but in our syllabus we have talked about only three methods. The first method is simple arithmetic method, the next is normal ratio method, and the last is power square method or inverse distance method. So the simple arithmetic mean, what you will do, you will just take the mean of remaining data sets and you will give it to the missing value. In normal ratio method, what you need is, along with your precipitation data series, you need the normal precipitation LCL. If you have normal precipitation data with you, you can go for normal ratio method. So this is the equation for normal ratio method. We have talked about M here. M is nothing but the number of rain gauges whose data are known to us, right? Then we have seen this example also. We haven't seen this example for that. We'll take an example for this in the next part. Then we talked about how you can take the average of rainfall series. So there are three different ways. The first is simple arithmetic average. Next is Thiessen polygon. You have to divide your area into multiple polygons, and then each precipitation or each rain gauge will have its own polygon, and you can multiply precipitation value with the average with the area value and divide by total area. You will get the average. And the next is isohedral method. So in the isoheight, what you will do, you will divide the area with multiple isoheight. Each isoheight will join the points of equal rainfall and you will have your area. So the only thing to remember in isoheight is you are going to work with mean of your precipitation, whereas in polygon, Thiessen polygon, you are not going to work with mean of precipitation. So that is the only difference in isoheight and Thiessen. Then we have talked about reciprocal distance square method or inverse distance square method. This is the equation, right? We know the distance in x-axis and y-axis, difference in with the missing value data. We'll calculate the d. We'll find the weightage, which is nothing but 1 upon d square, and using this equation we can calculate the missing data series, right? So now what we are going to do, we are going to take few examples so that we can practice it. It will help us to practice the numerical, and then by the end we are going to discuss the assignment 3 also, if you have some doubt in assignment 3. So these are like the 3 practice questions that I have taken. So the first practice question is based on your number of rain gauges, like we would like to know whether for this particular example whether the number of gauges that are given are sufficient or not. So let us solve this equation. So what we are going to do, we are going to first read the question here. So they are saying that a catchment has 7 rain gauge station. The average annual rainfall at stations are given in the table. Find the required number of rain gauges if maximum permissible error is 5% is needed in rainfall estimation, right? Then also at the same time they are saying if the rainfall at station G, which is 580, is recorded as 530 mm. So what will be the required number of rain gauges and why the required number of rain gauges has changed? See, so they have given us two cases. The first case is given in the table, and in the second case they are asking us to change the value of 580 with 530 and then calculate the number of rain gauges. And if there is some change in the number of rain gauges, they are asking why there is the number of rain gauges has changed. So what we are going to do now is we are going to take this solved exam. We are going to solve this example. So the first thing we need to do this is, the only thing we need to do here is we need to calculate the CV, that is coefficient of variation. So first we are going to take the mean of this data set, then we are going to calculate the standard deviation, and after that we are going to calculate the CV for first case, right? So let us take the mean of this sum for the first case. So when we are taking the first case and we are taking the mean for it, so for case 1, that is when precipitation at G is 580 mm, right? So the first thing which we are going to do is we are going to take the P bar, that is the mean of precipitation. So we are getting the answer as 721.28 mm. Now after we have calculated the mean, we are going to calculate the standard deviation value, which is sigma n minus 1. And how we are going to calculate that? We are taking the square root of P of individual precipitation minus P bar square divided by n minus 1. So this is the equation to calculate standard deviation, right? So when we are using this, we are calculating the standard deviation and it is coming as 85.88 mm. The next step is to calculate CV, coefficient of variation, which is nothing but ratio of standard deviation in, and if you want to calculate this in terms of percentage, we will multiply it with 100. So when we are doing that, we are getting the answer as 11.9. And now the next step is to calculate the number of rain gauges n. And how we can do that? We can calculate by using CV by error the whole square, this equation. So now what is this error? This error is nothing but the desired CV that they have given, which is 5% they have given. And the answer here is 11.9. So 11.9 divided by 5 the whole square, it turns out to be 5.67. So 5.67 means approximately 6 rain gauges. So number of rain gauges that are required are 6. So in the question they have given us 7 rain gauges. So 7 gauges, it means it's good only because the required number of rain gauges are 6. Now they are asking what if this G value is going to change and it is 530 mm. So what changes are going to come here, whether the number of rain gauges are going to increase or decrease. So let us see that. So for case 2, that is when G is 530 mm. So let us calculate the precipitation mean. So when we are calculating the precipitation mean here, the answer is 714.14 mm. Obviously the value of G is reducing, it means the precipitation will also get reduced. Second, we are going to calculate a standard deviation. Again the value of standard deviation. Now since the precipitation value is decreased, the standardization value will increase. So we are getting the value as 100.44 mm. The next term is to calculate CV. So CV would be 100.44 divided by 714.14 into 100. So the value of CV is 14 here, 14%. Since the value of CV is increasing, it means the number of rain gauges would increase. So the fourth term is N is equals to CV by error, the whole square. So 14 by 5, the whole square, it is giving us as 7.91, which means 8. 8 rain gauges are required. So now we can say that why the number of rain gauges are increased here, because the precipitation value got decreased, so it is eventually affecting the existing CV. So existing CV is increasing here. So whenever the existing CV is increasing, we can say that the desired number of rain gauges would increase. So we can say that in case 2, if there are only 7 gauge stations which are given, it means this condition is not going to work. In order to make this condition work, the number of rain gauges should be 8. It means there is a need of one more gauge station. So the extra gauge station that is needed is 1, because in the question they have given us 7 rain gauges, right? Yes, they have given us 7 rain gauge station. So in the case 1, it would work. But for case 2, when the precipitation at G got reduced, this arrangement would not work, because the required number of rain gauges are 8. So we are supposed to add one more station here in case 2. I hope this is clear now, how we are calculating whether the number of rain gauges are able to calculate the rainfall in a series or not, in a catchment or not. Now the next problem here, this problem is for Thiessen polygon method. So let us see how we can calculate this term. All we need to calculate is the average precipitation for this arrangement. So they are saying that there are 5 rain gauge stations A, B, C, D are located in square shaped hypothetical basin of side 29 km. The station A is at the center of the basin. Compute the mean aerial rainfall over the basin by using Thiessen polygon method if the rainfall at stations are respectively. So they have given us the rainfall. All we need to do is we need to calculate the average values. So how we are going to do that, let us see. So first we should remember the steps that are given in the Thiessen polygon, that we are supposed to do we are supposed to bisect each side, and we are supposed to form a triangle shape. So let us see how we can do that. So the question that was given to us was, there is a catchment each having 29 km, and we have rainfall arrangement here. The rainfall at center is A, B, C, D and E, right? So what we are going to do here is, we are going to mark the center of each side. This means we are dropping a perpendicular bisector from BC to DE, from BE to CD, from CD to BE, right? And we are going to connect it at A. Now we are going to connect all these sides. So we can say that the station which is at E, the rain gauge which is at E, is only going to account for this area, is only going to measure or record rainfall which is happening in this area. Similarly, the rain gauge which is at D is only going to measure the rainfall which is occurring in this area. Similarly for B and similarly for C, right? But when you look at A is going to account for the entire area which is happening in the center, for this entire area. A is going to account for this. So now we have 5 area and we have 5 rain gauges which are having precipitation record. We know the value of PA, we know the value of PB, PC, PD and PE. All we need to do is we need to calculate area of PA is A1, area for PB A2, A3, A4 and A5. So this area is nothing but A2, this area is A1, this is A3, this is A4 and this is A5, right? So all we need to do is we need to calculate the area. So how we can do that? If we know the area A2, it means we know the area A3, A4 and A5 all are same, right? So we want to calculate this area first. Once we know this, what we can do, we can calculate A1 as total area minus 4 times of A2, which will give us A1, right? So total area is easy to calculate. It is the square of 29 by 29. But what we need to calculate is A2. So how you can do that is, this entire side, this side and this side is 14.5 and this is 14.5, right? So this is nothing but a triangle. So this is the base, this is the height. We can say this is nothing but half into base into height. So we'll get the area of triangle A2, A3, A4, A5 by simply multiplying half into 14.5 into 14.5. This will give us the area A2, A3, A4, A5, right? So we know this area now. Now we are supposed to calculate A1. So A1 would be 29 ka square minus half into 14.5 into 14.5. So it will give us A1. So now you know A1 as well. So you know the entire area now and you know the precipitation value. Yes, we want to use Thiessen polygon, which will give us average. So the equation would be P of A multiplied by A1 plus P of B multiplied by A2 plus P of C multiplied by A3 multiplied by A5 divided by total area. The total area you know, now you can get the P bar value, which would be in centimeter. So now you can calculate this value and you can check. So the for cross checking, the answer here is 99.37. So if you want to calculate this, you can calculate later and you can cross check with this value. The answer should be 99.37 centimeter. The last sum that I have given is based on inverse distance method. So here what you can do is you can apply both the approach to find the missing rainfall at station A. You can also apply the inverse distance method and you can also apply normal ratio method, since normal rainfall is given to you. And then you can cross check whether the value that is coming for the rainfall at A is same or not. It would be somewhere around same. So let us see and solve this sum by both the equation, by both the method, that is by normal ratio and as well as by using inverse distance. So what they are saying here is the catchment has 5 rain gauge station. The normal monthly rainfall for August at this station is known. So the normal data series is given, right? And we know now like what is normal rainfall. So this 325 mm is nothing but the average of last 30 years, yeah, previous 30 years data series. And they have given us observed rainfall values at station B, C, D and E. And they are asking us to find the missing rainfall at station A. So what we are going to do, since we have the normal rainfall values for each station and only precipitation for A is missing, first method that we are going to use is normal ratio method. And also they have given us the distance. So since we know the distance between A and B, then we can use distance power method also. So let us solve this numerical by using both the approach, that is normal ratio and as well as inverse distance method. So the first approach that we are going to use here is normal ratio method. So normal ratio method, first we will like to write the equation for that. So the normal ratio method, since the P value of A is missing, it means P of A divided by normal ratio at A is equals to 1 upon M. That is, M means how many rain gauge stations values are known to us. So there are total 5. Out of 5 only one is missing. It means M would be 4. And here other rain gauges would come. So PD upon NB plus PC upon NC, PD upon ND plus PE upon NB. I think they have given us how many stations? They have given us till NF. So PF upon So this is the equation. Now the only missing value here is P of A. This is only unknown, and all other values are known to us. So what we are supposed to do, we are just supposed to substitute the values here. So P of A upon N of A. So the value of N of A is 325 equals to 1 upon M. So M means there are total 6 stations and only one station is having missing value, means 6 minus 1, so M would be 5. PB is 28 and NB is 306. PB means precipitation data, that is event rainfall, plus PC is 35 upon 301 plus 41 upon 390 plus 33 upon 366 and finally 23 upon 284. So if we solve this equation, we will get the value of PA. And that value of PA is coming to be 31.46 mm. So this is how we have solved this. We have just substituted the value and then we have got the value of PA as 31.46. So this was based on normal ratio method. Now let us see if you are going to use inverse distance method or power distance square method, what is the value of PA that is coming. It should be something which is closer to this value, 31.46. So let us do that. First we are going to write the equation for second method, that is inverse power distance method. So the main equation is, like for PA it would be summation of PI upon WI divided by summation of WI. Here PI is nothing but individual precipitation value for respected station, but we are supposed to calculate WI. And how we are going to calculate WI? So the term WI for individual rain gauge is 1 upon DI square, and DI square is XI square plus YI square, that is the resultant of resultant of your distance. So let us calculate DI for individual rain gauge station. So we are going to calculate DI for each station whose values are known to us. So first we are going to calculate it for dB square. So how we are going to do that for dB square? So let us see here. For B station, the x coordinate is 7.5. So we are going to take a reference as A. So we are going to calculate the distance between x coordinate of A minus y coordinate of B, x coordinate of B, and we are going to take the square of that. It means we are going to take 15 minus 7.5 ka square, this is nothing but xi square, plus similarly the difference between y coordinate of A and B, which is 15 minus 5 ka square, and this will give us dB square. So answer for this is 156.25 kilometer square. So same way we are going to do it for DC square. So for DC square, we will take the difference between x coordinate of A and C plus difference of y coordinate of A and C, and we are going to square of it. So for C it is 15 minus 5 square plus 15 minus 15 ka square, so it is 100. Then for D of D, then we are calculating it for D of E. So for D of D is 15 and x coordinate of D is 12 plus 15 and y coordinate of C is 21, D is 21. So we are getting an area of 45 square. Next we are going to do it for E. So x coordinate of A minus x coordinate of E ka square. So 15 minus 24 square plus 15 minus 13 square. So it is 85 kilometer square. And similarly for D of F, x coordinate of A is 15, x coordinate of F is 19 plus 15 minus 6 square, it is 97 kilometer square. So now that we have distance value for individual gauge station, it means we can calculate the individual weight for each station just by taking the reciprocal of it. So now we can calculate WA square, sorry, WB square, WC square, WD, WE and WF. It is nothing but 1 upon dV square, 1 upon dC square, 1 upon dd square. So you can calculate this value, or else what you can do is you can simply substitute the values in the equation, and the equation is P of A was missing, which is nothing but summation of Pi into Wi upon summation of Wi. So first we substitute the value of Pb into W of B plus Pc into W of C right, divided by total W. Now we know the value of Pb. The value of Pb is 28. So 28 into Wb is nothing but 1 upon dB square. So the value of 1 upon dB square is 1 upon, means 1 upon 156.75 plus PC is known to us, it is 35, and WC is 1 upon DC square, it means it is 1 upon 100 plus 41 upon 1 upon WD, and 2 WD means 1 upon DD square. So DD value is 45 plus 33 upon 85, and similarly 23 upon 97. And similarly we'll divide it by total W, so 1 upon 156.75 plus 1 upon 100 plus 1 upon 45 plus 1 upon 85 plus 1 upon 97. So we have directly substituted the value in the equation, and here we are getting the answer of PA as 33.87 mm. So now we have calculated the missing value using both the approach, that is by inverse distance square method and also by using normal ratio method. So using inverse distance the answer is coming 33.87 mm, and using normal ratio method the answer is 31. So it is near about, there is only difference of 2 mm, so it means it is quite close. So in this way we can calculate the missing data using either of the approach depending upon the given data set that is there for a problem. So now that we have practiced some of the questions, now what we can do is we can look into the assignment questions also, right? So now they are saying that there are, in each assignment there are 10 questions, right? So they are asking us some theoretical questions also. So in order to solve the theoretical question, what I would suggest is you should go through the live videos or recorded videos that are there on the portal, and also for few of the questions you can take the help of the session that we have just doing. So I'll be uploading the session onto the log sheet, and from that you can access, and you can, by looking at the session, you can mark the respective questions. So if we know that there is a non-recording type of rain gauges and what it is called. So the answer is, I won't disclose the answer here, but we have covered this in the session today. There are only two types of gauge stations, recording and non-recording, and non-recording is also known as what type of station. Also we have look at into the mass curve of rainfall. So what does curve of rainfall give us to us? We have discussed in the today's session also. Then what is rain gauge density? So this is the first definition that we have covered when we are studying rain gauge network. Then which of the following term is not used to designate a rain gauge? This for this you can use the trial and error method, like you can eliminate the values. So if you look into anemometer, you can look into pluviometer, you can look into ombrometer and hytometer, and you can eliminate like which of them is not used to designate a rain gauge. Then how many types of rain gauges are there? We already know this, like how many types of rain gauges are there. We have discussed this. Now, in order to cover this, the friction between raindrop and surrounding air is due to. You have to look into the atmospheric vapor, like we have shared the link with you. So if you go and revise that, or you look into the video, you would come into the conclusion like what is the perfect answer to this, right? I've covered this in the previous class, which was about atmospheric water. So I've uploaded like two videos for that. That is part 1 and part 2. So part 1 is based on the theoretical part. So if you look into that video, you will get to the answer for 7th question. Now when we talk about question number 8, so this is like very simple, since there is already the data set given to us. Hello. So already.
The third question is due to gravity force or traction. That's what.
Sorry Naga, your voice is not clear. You can ask into the chat box also.
In the seventh question, the
You are asking about the first question, Naga. Seventh question. Okay, so you have any doubt in seventh question? See, if you want to solve the seventh question, gravity of friction drag, the thing is, Naga, we are not supposed to give you the answer for the assignment questions. But what I can give you is a small hint. So if you want to know the answer for this question is, you can do two things. Either you can go and look into the recorded video session by Dr. Shrija, and you can see the part where she has derived terminal velocity equation. So during terminal velocity derivation, she would have discussed about which is the part that covers the friction between raindrop and surrounding air. Or also in our previous session, like that is the week 2 interactive session, I have discussed about this. So if you look into the first video that I have uploaded, you can come to the conclusion of this answer. I cannot give you the answer directly because still we have one more day to submit the assignment. So directly I can't give you the answer. You can go and look into the videos, you just have to cover the terminal velocity part. I don't know about this, Naga, like whether all of the subject assignment is directly available. If it is directly available, you can check it once for if it is available or not for this subject. The eighth question is very simple. You just have to use the Thiessen polygon equation, P bar. So they have given rainfall for individual station and they have given the respective area. You are not even they haven't even asked you to calculate the area also. You just have to multiply and add and divide by the total area. It will give you the final answer. Just make sure that the answer is in centimeter. So the rainfall is in centimeter. It means the final answer would also be in centimeter. So that is not a thing to worry. The next they have asked is the isohyet for monthly rainfall over a catchment is given below. The average precipitation over the catchment using isohyetal method is. So here they have given the rainfall. So while we were discussing isohyet, I have told you like whenever you are taking isohyet, the important thing is to calculate the mean of rainfall. So what you are going to do, you are going to add one more column here, which will give you the mean rainfall, and you will calculate the mean rainfall for each isohyet, and then using the formula you will multiply the mean rainfall with the corresponding isohyet area and divide it by total area. You will get the average rainfall. Now the next approach is using normal ratio method. So this is the now this certain kind of question we have just solved. They are saying is The station A4 is inoperative, but they have given you the normal rainfall as well as the precipitation rainfall, like that is the event rainfall. So all you are going to do is you are going to just use the equation, that is P of A4 divided by N of A4 is equals to 1 upon M equals to bracket the other term, and then you are going to solve it for P of A4 and you will get this value of inoperative station. So I think if you go and look into the videos or the session that we have discussed today, I think you would be able to solve the assignment 3s quite easily, because I don't find any of the question in the assignment 3 really difficult. So I hope this session is helpful. We have covered everything in the session. You just have to just do a revision of your concept and then you can start solving your assignment question. Apart from this assignment question, do you have any other question? So let us check once again whether we have covered everything. We have started with thunderstorm cell model, where we have discussed about the intensity of rainfall, like how using thunderstorm cell model we can calculate the intensity of rainfall. Then we have looked into an example of thunderstorm cell model where we have calculated the uh, parameters at the ground scale as well as at elevation of 700 meter and 9500 meter, and then we have taken the average of intensity of rainfall and we got to the answer, like we have seen this problem. Then we discussed about different forms of precipitation. We started with liquid form of precipitation, that is drizzle and rainfall, and then we talked about few solid form of precipitation, that is glaze, hail, snow and rim, right? So we talked about this, and each of the form of precipitation, like the liquid one, depends upon the size. If the size is very small, that is less than 0.5 mm, we can say that it is drizzle, but if the size is between 0.5 to 6 mm, we say that it is rainfall, right? So the important form of precipitation that is there in our syllabus is rainfall. So the next thing that we talked about was how we can measure the rainfall. So we came into we talked about different types of measuring instrument. The first were instrument based measurement of rainfall. So there are only two types of rainfall. We know recording and non-recording gauges, right? We know how non-recording gauges work. We know how recording gauges work. Then what are the output given to us by recording rain gauges? Either it could be accumulated data series or it could be a mass curve, right? Depending upon the type of recording rain gauges, whether it is weighing bucket or tipping bucket. Then we saw how radars are used to measure the rainfall. Then we looked into how automatic rainfall stations are there, right? Then after we studied like how if there are we talked about what is rain gauges network, right? And what are its significance. So if we know like in a catchment there are certain number of rain gauges, how we can calculate whether that rain gauges would be F is sufficient or not. So based on the coefficient of variation value, whether the CV value is less than 20% or not, we can conclude whether the stations are there is a need of station or not. And we have also seen few example of based on this method of CV. Then we talked about how we can present the rainfall data, whether there is spatial representation and whether it is temporal representation. For spatial representation we talked about isoheights, and for temporal representation we talked about histogram, which gives you rainfall depth versus time, or we talked about hydrograph, which gives you rainfall intensity versus time. Then we saw how mass curve gave us the accumulated rainfall versus time, which is nothing but a increasing curve, right? Then we talked about analysis of rainfall, like if there is some missing data, how we can account for those missing data. So there are different techniques, but in this session we talked about only three techniques, right? So those three techniques were either we can go for a simple arithmetic average, or we can go for normal ratio method, or we can go for inverse distance method, right? We also saw numerical based on normal ratio method and also inverse distance square method. Then we looked into how we can take the average aerial rainfall. So there are three techniques. First is simple average, arithmetic mean, or next you can do is you can divide the area into number of polygons, and then you can multiply the precipitation value coming into that area, and you can take the weighted average, and that will give you the average precipitation value using Thiessen polygon. Or you can use isohedral method, right? What you can do, you can join the points having equal rainfall depth, and those lines are called as iso height, and you can divide your area, total catchment area, into different areas, right? And then using the mean precipitation value, you can calculate the mean precipitation for entire area. So you can use this formula here to calculate isotope method. Then after that, what we have done is we have calculated the rainfall values, right? We have taken few examples and we have calculated, and at the end we have discussed the assignment also. So I can say that we have covered everything, and now we can conclude today's session. I hope the today's session was also informative like previous two session, and I'll be uploading and sharing the notes of this onto the Google Drive so that you can revise, and also by using the link you can solve the assignment 3 questions. So that is from my side. Thank you.